Chapter 3, Lesson 2 on page 80 is titled The Simplest Matter. On the left-hand side, it describes what you'll learn. Students will describe the relationship between elements in the periodic table, explain the meaning of the atomic mass and atomic number, identify what makes an isotope, and contrast metals, metalloids, and non-metals. Let's get into it. The elements. Have you watched the television today? TV sets are common, yet each one is a complex system. The outer case is made mostly of plastic and the screen is made of glass. Many of the parts that conduct electricity are metals or combinations of metals. Other parts in the interior of the set contain materials that barely conduct electricity. All of them are different materials, have one thing in common. They are made up of even simpler materials. In fact, if you had the proper equipment, you could separate the plastics, glass, and metals in these simpler materials. One kind of atom. Eventually, though, you would separate the materials into groups of atoms. At that point, you would have a collection of elements. An element is a matter made up of only one kind of atom. At least 110 elements are known, and at least 90 of them occur naturally on Earth. These elements make up gases in the air, minerals in rocks, and liquids such as water. Examples of naturally occurring elements include oxygen and nitrogen in the air that you breathe, and the metals gold, silver, aluminum, and iron. The other elements are known as synthetic elements. These elements have been made in nuclear reactions by scientists with machines called particle accelerators, like the one shown in Figure 10. Some synthetic elements have important uses in medical testing and are found in smoke detectors and heart pacemaker batteries. Elements are matter made up of only one kind of atom. There are 115 known elements. 90 of them are naturally occurring elements, plus the synthetic elements that are made by scientists. So 90 things have been naturally created, and then about 20 to 25 of those have been created by scientists through different types of scientific methods. Here's a picture of how those elements are organized. Because there are so many of those, 115, we've got to find a way to put these things together. In the course of history, scientists have found the common properties that these items have and the common ways in which they're organized by the structure that they have in terms of the protons, the neutrons, the electrons, and they've created this table to keep them organized. This will show you the different types of families. So this orange right here, pillar, this column, is the alkali metals. All of these metals are really similar to each other. In the next one, you've got the alkaline earth metals. This is a family of elements. All these really react and behave in a similar fashion. This big, huge section in the middle are called the transition metals. Here you've got poor metals, other non-metals, and then you've got noble gases, and you've got a different set of lanthanoids and actinoids down here that we'll spend a little bit of time learning about. Mostly, we're going to understand how this periodic table came to be organized and how we're going to use it in science to learn more about the world that God created. The periodic table on page 81. The periodic table is organized in rows called periods that have the same number of energy levels, and the periodic table is organized in columns. Remember, columns are things that stand up vertically, so I always remember columns as something that's going up and down. Those are our groups. These groups have similar structures that form similar bonds. If I go back to the picture, columns are going up and down, rows are going across in this lateral way. Periodic table on page 81. Let's read. Suppose you go to a library like the one shown in Figure 11 to look up information for a school assignment. How would you find the information? You could look randomly on the shelves as you walk up and down rows of books, but the chances of finding your book would be slim. To avoid such haphazard searching, some libraries use the Dewey Decimal Classification System to categorize and organize their volumes and to help you find books quickly and efficiently. Charting the elements. Chemists have created a chart called the periodic table of elements to help them organize and display the elements. Figure 12 shows how scientists changed their model of the periodic table over time. On the inside back cover of this book, you will find a modern version of the periodic table. Each element is represented by a chemical symbol that contains 1 to 3 letters. The symbols are a form of chemical shorthand that chemists use to save time and space on the periodic table, as well as in the written formulas. The symbols are an important part of the international system that is understood by scientists everywhere. The elements are organized on the periodic table by their properties. There are rows and columns that represent relationships between the elements. The rows in the table are called periods. The elements in a row have the same number of energy levels. The columns are called groups. The elements in each group have similar properties related to their structure. They also tend to form similar bonds. Periodic table is a chart that organizes and displays the information about the elements. The atomic number is the top number in the element's periodic table block, and this is what identifies that element from other types of elements, and it also identifies the number of protons that happen to be in that element's nucleus. This tells the number of protons in the nucleus of each atom of that element, and the number of protons remains constant in every atom in an element. On page 83. Identifying characteristics. Each element in different has unique properties. These differences can be described in part by looking at the relationship between the atomic particles in each element. The periodic table contains numbers that describe these relationships. If you look on page 82, you can kind of see how scientists started to develop over a period of time the different types of characteristics that they were noticing from different types of materials. And from these different types of tests, they started to develop this way to classify these items. Today, science has moved further into the future to identify more and more characteristics of these different items and now have been better organized in the periodic table. Here's how those things are organized based on these identifying characteristics. Number of protons and neutrons. Look up the element chlorine on the periodic table, found on the inside back cover of your book. So on the very back page, if you open all the way up to the back and then just have the cover open, that should be where your periodic table is. Look for the symbol CL. Cl is the symbol for chlorine, as shown in figure 13. But what are the two numbers? The top number is the element's atomic number. It tells you the number of protons in the nucleus of each atom of that element. Every atom of chlorine, for example, has 17 protons in its nucleus. If you're looking at the top corner of page 83, you can see where that chlorine is highlighted and it pops out. It says chlorine, 17, Cl, and then 35.453. 17 is the atomic number, and it tells you the number of protons in the nucleus of each atom of that element. Here's an example. The element name is identified at the top of the block. The atomic number is then listed. Here you have the chemical symbol, which identifies the element, and then you have the atomic mass. This is the weighted average of the element's isotopes. We're going to learn about isotopes in our next two paragraphs. Isotopes. Although the number of protons change from element to element, every atom of the same element has the same number of protons. However, the number of neutrons can vary even for one element. For example, some chlorine atoms have 18 neutrons in their nucleus while others have 20. These two types of chlorine atoms are chlorine 35 and chlorine 37. They are called isotopes, which are atoms of the same element that have different numbers of neutrons. So basically, if you're adding a proton to any type of atom, it's going to change what atom it is. For example, the element that has one proton is hydrogen. If you add another proton, it is helium. If you have another proton, it's lithium. If you have another proton, it's beryllium. If you have another proton, it's boron, then carbon, then nitrogen, then oxygen. Now I'm just going up and down the periodic table. That's from 1, 2, 3, 4. But if you add a neutron, nothing changes, technically. The neutron doesn't decide what type of atom or what type of element it is. The neutron is adding that neutral charge to our nucleus, and there can be a different number of neutrons that are going to be in an atom. Normally, atoms are going to operate in what we call a neutral position, so there's usually the same number of protons as neutrons as electrons. The time where it becomes an isotope, as we're reading about right now, is where you have more neutrons than normal. So if the chemical number is 17 for chlorine, it's got 17 protons. Here it describes 18 neutrons and 20 neutrons, so two different numbers of neutrons that don't necessarily always match up. You can tell someone exactly which isotope you're referring to by using its mass number. An atom's mass number is the number of protons plus the number of neutrons it contains. The numbers 35 and 37, which were used to refer to chlorine, are mass numbers. Hydrogen has three isotopes with mass numbers of 1, 2, and 3. They are shown in figure 14. And each hydrogen atom always has one proton, but in each isotope, the number of neutrons is different. So one proton is hydrogen, that's protium. One proton and one neutron is deuterium, that's also hydrogen, but it's got that extra neutron. And then you've got tritium, which is one proton of hydrogen and two neutrons. Isotopes, atoms of the same element with different number of neutrons. Your mass number is the number of protons plus the number of neutrons. So you add those two items together. The atomic mass is the number found between the element's symbol. If I go back, this is the atomic mass. That's the weighted average of the mass of the element's isotopes. We take those different isotopes and we find an average weight. That's what we find as the atomic mass. Atomic mass on page 84. The atomic mass is the weighted average mass of the isotopes of an element. The atomic mass is the number found below the element symbol in figure 13. The unit that scientists use for atomic mass is called the atomic mass unit, which is given the symbol U. It is defined as 1/12 the mass of a carbon-12 atom. The calculation of atomic mass takes into account the different isotopes of the element. Chlorine's atomic mass of 35.45 U could be confusing because there aren't any chlorine atoms that have that exact mass. About 76% of chlorine atoms are chlorine 35, and about 24% are chlorine 37, as shown in figure 15. The weighted average mass of all chlorine atoms is 35.45 U. So the atomic mass is the number found below the element symbol. It's the weighted average mass of the atom of an element, and the unit used for the atomic mass is the atomic mass unit U. In the next section on page 84 and 85, we're going to look at the classification of elements into the different groups. You can tell in the back of your book that this classification is being made in the same way that's displayed on your screen right now, that these three different colors represent three different types of elements, and those types of elements are going to distinguish how they behave and the properties that they share because they are different types of elements altogether. On page 84, the classification of elements. Elements fall into three general categories: metals, metalloids, and nonmetals. These elements in each category have similar properties. Metals. Metals generally have a shiny or metallic luster and are good conductors of heat and electricity. All metals except mercury are solid at room temperature. Metals are malleable, which means they can be bent and pounded into various shapes. The beautiful form of the shell-shaped basin in figure 16 is a result of the characteristic. Metals are also ductile, which means they can be drawn into wires without breaking. The word ductile means that they can be turned into a wire. If you look at the periodic table, you see that most of the elements are metals. That's the larger blue section on the screen. Other elements on page 85. Nonmetals are elements that are usually dull in appearance. Most are poor conductors of heat and electricity. Many are gases at room temperature. Many are gases at room temperature, and bromine is a liquid. The solid nonmetals are generally brittle, meaning they cannot change shape easily without breaking. The nonmetals are essential to the chemicals of life. More than 97% of your body is made up of various nonmetals, as shown in figure 17. You see that except for hydrogen, the nonmetals are found on the right side of the periodic table. Last one is metalloids. Metalloids are elements that have characteristics of metals and nonmetals. On the periodic table, metalloids are found between the metals and nonmetals. All metalloids are solids at room temperature. Some metalloids are shiny, and many are conductors, but they are not as good at conducting heat and electricity as metals are. Some metalloids, such as silicone, are used to make the electronic circuits in computers, televisions, and other electronic devices. Elements fall into three general groups characterized by similar properties. Metals, which is most of all the elements. They have shiny luster. They're good conductors of heat and electricity. Most are solids at room temperature. They're malleable, which means that they can be shaped and changed into different shapes. And they're ductile. It means they can be drawn into a wire without breaking. 2. Nonmetals. Found on the right side of the periodic table. They're dull in appearance, poor conductors. Many are gases at room temperature. They're brittle, means they can't change shape without breaking. 97% of the human body is made up of these non-metals. Last one is metalloids. Metalloids are found between metals and non-metals on the periodic table. They have characteristics of both metals and non-metals. They do not conduct heat and electricity as well as metals. All are solids at room temperature. That summarizes our study of the classification of elements.